Hello, Stat 300, and this is Professor Gonzalez, and I'd like to do some problems from the assignment side of Alex. The assignment side of Alex, and this is homework problems from 10.2. Okay, now 10.2, we're taking a look at building a confidence interval using two samples, two proportion samples, two samples of sample proportions, rather. And so this is a little bit different than the other confidence intervals. You will see a lot of overlap, a lot of similar ideas, but we're taking a look at we're looking at two samples and gathering two sample proportions. So that does make it a little more confusing in some ways. Let's go ahead and take a look at our formula sheet just to kind of do a little bit of reviewing here. If you remember back in chapter 7 here, we had a sample proportion. So this p hat, let me see if I can highlight this. This symbol right here, p hat, means sample proportion. Let's do that, sample proportion. So that p hat means sample proportion. Now when we just had a p right here, this was the population proportion. So P is a population proportion, and P hat with that tiny little crown like a hat, I guess, is the symbol or the variable that we use that represents the sample proportion. Now the sample proportion is made up of this x value up top, and that x value just means the number. I should zoom in. Number of individuals in number of individuals in the category of interest. Okay, that's what X is, the number of individuals in the category. So let's say I was doing a sample proportion and I decided to just, let's say we did a simple random sample and it happened to be my class. That's not really a simple random sample. But anyways, let's say I pulled my class and asked them, how many of you wear glasses? And so X would be the number of individuals in the category of interest, the number of individuals that wear glasses. Now N would be the sample size, in this case the size of the class. Whoops, that really is large. Sample size. Why is that so large? Somehow that didn't trigger. Okay, so anyhow, that's something I wanted to review there, that our sample proportion is p hat, and x is the number of individuals in the category of interest, and n is the sample size. That's real important for us to know. Okay, let's get on back over to the beginning of this whole thing, right here. And this says, please construct, oh, and there's more that we need. Darn it, I need to get back to that right there. Okay, so this is 10.2, and here we are looking at the confidence interval for the difference between two proportions, okay? The difference between two proportions, where'd that go? So I want to break this formula down. Now this thing really looks like a real beast here. Whoops. And I want to break this down. So in the middle here, notice this is P1 minus P2, and it's not a hat. So this is the difference of our population proportion 1 minus population proportion of sample 2. So this is from the population. And with these confidence intervals, very often what we're trying to do is we're trying to figure out, we don't know what the difference of these two populations are, the proportions are rather, in the population. Let me say that again. We don't know what this value is. It is the proportion proportion 1 minus proportion 2. So it's the population proportion from two different samples. I don't know what that difference is. So what I do is I go ahead and get myself a point estimate, which is like the next best thing, right? So a point estimate would be, well, if I want to know what my population proportion is from sample 1, why don't I get, I'm sorry, if I want to know what my population proportion is for my first population, the next best thing is to get a, let's see, sample proportion, or get a sample. Wow, that is, I don't know why things are not lining up here. The next best thing is to get a sample. So when I take a sample from my first, so I look at the proportion p hat, so it's a sample proportion for my first sample, and my sample proportion for my second sample. I take the difference. This is called a point estimate. It's called a point estimate. Okay. Now, there's some other things I'm going to need. I'm going to need, see if this is working. Yeah. I'm going to need, and you'll notice, you'll remember this from confidence interval from 8.1 and 8.2. I need my critical value. Now this is the critical value, and we're using z values, and you can recognize this is z sub alpha, half of alpha rather, and that's just going to be, all you have to do is take a look down here. Like for instance, if they said, I want you to find me a critical value for a confidence level of 99.5%, that's a confidence level. You just go to the confidence level of 99.5, and your critical value, that would be your critical value, would be 2.807. Okay, so that is really easy to get with this table. That couldn't really get much easier than that. But here's really the hard part. So the hard part is finding this piece right here. And that piece is called, whoops, let's see, let me try that again. The hard part is finding this piece right, oop, struggling today. This piece right here, which is called standard error. Whoops, standard error. So standard error is this big beast of a problem that you've got to get. By the way, that standard error was in our other formulas from 8 point, let's go back to, this is 8.1. In this particular problem, we had our point estimate right there. We had our critical value right there, so you can see that's the same. It's just that we've got, the difference of two different proportions. And then this guy right here was much simpler, but that is your standard error. Okay, so there's definitely some real similarities, but it's just that in this case, it's a proportion, and the proportion formula is a little more difficult. And then we also have proportion from sample 1 and proportion from sample 2, so it gets more complicated. And let's put a final touch on this. When you multiply the critical value times the standard error, you get the margin of error. So those are the important little pieces. Now, you can see that we've got these inequalities, right? So what we're trying to do is, we don't know what this population, the difference of the population, the proportion of population 1 minus the proportion of population 2, we don't know what that difference is, but we're trying to get a lower bound and an upper bound to say it's in between this with a certain level of confidence. So of course, when you calculate this whole thing over here, this is the lower. And when you calculate all this up here, this gives us the upper. And we're hoping to squeeze what we're trying to figure out, the difference of population population proportion 1 minus population proportion of 2. We're trying to figure out what that number is and squeeze it in between our interval. Okay. All right, so let's go ahead and see if we can do this first problem. We've got 3 problems to work on now. Go to problem number 1. And problem says construct an 80% confidence interval for the difference of P1 minus P2 when x sub 1 equals 17 and n sub 1 equals 31. So this is just the subnotation. I know what I'm going to do is I'm going to go ahead and use some colors here because I think that's just really helpful for our eyes to see what's going on here. I'm basically coloring this stuff from our first sample, from our first population proportion, and also then our sample. Okay, and then let's go ahead and make green our second population, and then remember what x is. Remember what x is? X is the number of individuals in the category of interest, right? From our second sample, and n sub 2 is our sample size. Okay, so with this information, we can start figuring out some stuff, and we do need to begin to write down. I'm going to just try to stick with the same coloring here. So let's go ahead and first figure out what is p hat from our first sample. Well, that is going to be it's going to be the proportion of our x sub 1, which is the people of interest, 17, out of the sample size on the first sample, which is 31. And we divide that and we get kind of a long, a number that we'll go ahead and round it to 3 places. How about 0.548? 0.548, okay? Now let's go ahead and switch on over to our second sample. Now we're looking for the sample proportion from our second sample, and we can see that the number of individuals in the category of interest is going to be, on our second sample, 13. And it's out of what's the sample size? 40. Excuse me. So I go ahead and divide that, and I get 0.325. Okay. So now what I want is so you can go back to the formula sheet to kind of remind yourself of the things we need. What I need to get next is I need a point estimate. Okay, I need a point estimate. So how do I get the point estimate? It's just the difference of those 2 samples. So let's go ahead and get that point estimate. Let's go back up here and find our point estimate. And our point estimate, of course, is just going to be sample proportion from the first sample minus the sample proportion from the second sample. So let's write that down. What was that sample proportion from the first? That was 0.548. What was the sample proportion from that second sample? That was 0.325. And then when we subtract the 2, we get that equaling 0.223. I'm going to put a circle around that. That's my point estimate. Okay, so we're just kind of picking away the little pieces that we need. I've got my point estimate right here. The critical value is going to be really easy because we just looked that up. Let's tackle this difficult standard error. Okay, that's the tough one. So the standard error is going to be this square root of what? Well, it's going to be the square root of our sample proportion of our first, oops, I guess I need to back off so I can see it. So that is just going to be right here, my sample proportion from my first sample, which is 0.548. Now that needs to be multiplied by its complement, which is just 1 minus this 5.48. So if I say 1 minus that, I get 1.452. And that needs to be divided by the sample size of that first sample, which is 31. And then I go ahead and add that. I do the same thing with my second sample. So that second sample proportion happened to be 0.325. Now we need to multiply that by its complement, which is 1 minus 0.325, 1 minus the green, which gives us 0.675. This needs to be divided by the sample size of sample number 2, 40. Okay. So I would recommend leaving this stuff in the calculator because, you start losing decimal values because it's just hard to type everything in again. I just went ahead and calculated this, left it in the calculator, added to, then calculated this. Just be really careful with your parentheses, making sure that this stuff on top and this is on the bottom. And then you should be able to calculate that. When I did that, I'm going to show you my results just so you have something to double check yourself with. I got approximately 0.013474 5685. Okay, and then I just punched the square root button, and that gave me 0.1160800, kept on going. So I went ahead and used 4 decimal places, 0.1161. Now remember, that's my standard error. Now the next thing we want to do, so let's just, since this is the first time doing this, let's continue to go back to that formula and see what we're picking off here. We just got the standard error, right there, standard error. Now we need to multiply it by the critical value to get the margin of error. And we're getting close to finishing this thing off here. We would like to get the margin of error. And we can get that by multiplying, remember that critical value, z sub half of alpha. And you get the critical value by looking at our critical level. What's our confidence level, rather? 80% it says right here. 80% confidence level. I'm going to write 80% right here. And it's very easy to find its critical value from that. You just go down to our handy dandy little chart and look up 80%. Here we are right here. We're going to look up with purple 80%. 80% has a critical value of 1.282. So 1.282. That's the critical value for an 80% confidence level. So how do you find the margin of error? Well, the margin of error, I'm going to put M for margin of error. The margin of error is going to be the critical value times the standard error. And the standard error we found right over here. So that's 0.1161. And when I multiply that together, I get approximately 0.1488. There's my margin of error. Okay, so now remember, let's go down to the formula. So remember how this works. I've got my sample, I've got my population proportion. Actually, let me just go up here and just start writing this out. And remember that the left-hand side is just a duplicate. The only thing that's different is we are subtracting the point estimate minus our margin of error. And then on the right side, we're taking the point estimate and we're adding right there, okay? So that's the difference. Let's go ahead and see if we could finish this off and squeeze it in here. Looks like we've got a little bit of space. So how would I do this? I would start, okay, my population proportion from the first population minus the population proportion from the second population, okay? And I think I'm gonna have to move that down because I'm a little bit tight over here. So let's just go like that. Okay, perfect. Now remember, what do we have on the upper bound? How do we figure out the upper bound? Well, you take the point estimate, which is right here, 0.223. The point estimate is just an estimate of that, right? It's just a point estimate, it's just an estimate of that, but it's not perfect. So we're going to give it a margin of error, and we figured out the margin of error. The margin of error was just this guy right here. So the upper bound is going to be point estimate plus margin of error. And we add those together, we get 0.3718. And we want to get the lower bound. Well, the lower bound is just the point estimate, which is the same thing, 0.223, minus the margin of error, 0.1488. And when we calculate that, we get to 0.0742. It said please round to 3 decimal places, so we'll do that. So this is going to be 0.074. The difference of my population proportion from the first population second proportion is going to be in between 0.074 and the upper bound is 0.372. And that is my confidence interval. And that's at an 80% confidence level. Okay. All right, let's do the next one. So we got 2 more. Procedure's the same. This one's a little bit tougher because we have to dig through the word problem to figure this out. They do have some nice little clues though. We're going to use the same color system in the same formula, of course. So let's see if we can do this. It says traffic accidents. Traffic engineers compare rates of traffic accidents at intersections with raised medians with rates at intersections with two-way left turn lanes. They found that out of the 4,649 accidents at intersections with raised medians, 2,280 were rear-end accidents, and out of 4,582 accidents at two-way left turn lanes, 2,174 were rear-end accidents. Man, that's a lot of information there, right? So something that I want you to really key in on is it's nice this book defines the population proportion from the first population. Let's let P denote the population of accidents of rear-end type intersections with raised medians. Okay, so we want let P, because this will help us a lot just kind of get organized. Let P be the accidents, the population proportion of accidents with rear-end type intersections with raised medians. Okay, well, let's see if we could find that. Where's that out up here? Well, it says they found that out of 4,649 accidents at intersection with raised medians, 2,080 were rear-end accidents. Okay, good. So that's my P1 information. That's the sample for P1. So P1. So I'm going to get my sample proportion. So P hat sub 1 from that. And now I'm going to use green for the next. And this is and out of 4,582 accidents at what kind? Not the raised medians. This is the two-way left turn lanes. 2,174 were rear-end accidents. Okay, and so let me color coordinate this down here. Right, so population of the second population is green, and my first population proportion is red. So I need to get my sample data, and this is, remember it says traffic engineers compared rates of traffic accidents at an intersection with raised medians. Okay, let's see, where am I gonna? Okay, let's get down here. It says part A. Assuming these two be random sample of accents from the two types of intersections, construct a 99% confidence interval for the difference between the proportions of accents that are of the rear end type and the two types of intersections. Okay, so we let P sub 1 denote the proportion of accents of the rear end type intersections with raised medians. So we already know that. Okay, wow. Okay, that was a little rough. Let's go ahead and take a look at my sample data. My population, so my sample proportion for my first population is going to be found by that information that I highlighted in red. It says that 2,280 were rear end accents, and this is of the raised median type. So the stuff of interest was 2,280, and it's out of a total of, there it is, 4,649. Now I divide that on a calculator and I get approximately, what, 0.490. Let's go ahead and get our sample proportion and our information for our sample proportion for our second sample. And that says out of, so that's the sample size, 4,582. Out of accidents of the two-way left turn lanes, 2,174 were rear end accidents. And so I calculate that. When I calculate that, I get 0.474. Okay, so we're trying to get a confidence interval that includes this difference. Okay, so the very first thing we want to do is we want to get a point estimate. And the point estimate that we're going to get, the next best thing, right? Remember, this is the population, but we can also go to that first population and sample from it. So we get a sample proportion from that first population. And we get that, whoops. And so what do we want to do to get our point estimate? We want to subtract the two samples, one from the first sample and then one from the second sample. And when we do that, right, we know that our sample proportion for our first is going to be 0.490 minus the sample proportion from our second, which there it is right there, 0.474. And when I subtract the two, I get my point estimate. I probably should have written that there. Let's call this and label it. This is called our point estimate. So our point estimate, when we subtract those two, is 0.016. Point estimate. Next thing, well, let's just tackle that beast, which is the standard error. Well, the standard error is this big square root that we've got to deal with. And remember, so we start off with our first sample proportion, and that is that guy right there. So it's going to be 0.490 times its complement. So 1 minus 0.49 is 0.51. This is all divided by our first sample size, which there it is right there, which is 4,649. Let's go ahead and add that to the information from our second sample. The sample proportion from our second sample is 0.474, and we need to multiply that by its complement. So 1 minus that green stuff is now 0.526. That gets divided by our sample size from the second sample, which was 4,582. All right, so we throw that in the calculator, and I'll show you just some of this intermediate stuff just so you can kind of see and match what you have. .000, 3 zeros, 1 0, 8 1, 6 7, dot dot dot. And when I take the square root of that, of course these are approximations, I get 0.0104, and that is my standard error that I need to use. Okay, now over here, what I want to do is I want to find my margin of error, and we can use M for that. We need our critical value, and let me use another color for that. Remember, our critical value is z sub half of alpha, and our critical value comes from our confidence level, 99.9%. So I'm going to look that up. I can go ahead and go to my formula sheet. 99.9 has a critical level of critical value of 3.291. 3.291. Okay, and that, all we need to do is multiply it by the standard error, which is right here. We did a lot of work to get to that, 0.0104. You multiply those two together and we get approximately 0.0342. Okay, great. We've got the margin of error, which is super important, and we've got our point estimate. Those two pieces are really going to get it done for us. We want to see if we can get a really good confidence interval that includes this 99.9% of the time, almost 100% of the time. And that speaks to the population proportion. But of course, to do that, we had to look at its sample, get a point estimate from a sample proportion. So it turns out that the point estimate right up here is 0.016. To get the upper bound, I have to add it to the margin of error, 0.0342. And I'm going to do that calculation. And then down below, I get my point estimate again of 0.016. And I subtract it from the margin of error of 0.0342. And I calculate that. And so when I run the calculation, this lower bound, I get negative 0.0182. And the upper bound I get 0.0502. Now this book is saying rounded to the nearest 3 decimal places, or at least 3 decimal places. So I'll go ahead and round it down to 0.050. And over here, this is negative 0.018. And that's the 3 decimal places. Whoops, less than symbol. That's my confidence interval at what, a 99.9% confidence level. Okay, so now, and there's something else that this book, it talks about, but it doesn't, I don't know, we need to talk about it, and that's assumptions with this kind of problem. So there are some assumptions that are being made here to make sure, to allow us to do this. It says the method just described requires the following assumptions. Well, the first assumption is that we have 2 independent simple random samples, and it did say that in the problem. Each population is at least 20 times as large as the sample drawn from it. I think that one sometimes is kind of hard to tell because, not exactly sure how big the population is, but if we're talking about the population of the United States or something like that, certainly 20 times the sample. So each population is at least 20 times as large as the sample. So if we took the sample multiplied by 20, if this was coming from a population in the United States, we'd be in really good shape. But that gets a little dicey sometimes because if it doesn't say exactly what the study was representing is the whole population. And then number 3, the individuals in each sample are divided into 2 categories. Yes, There were definitely two different categories. What were those categories? There were accidents at intersections with raised medians, and then the other one was accidents at intersections with two-way left turn lanes. Okay, so that is satisfied. And then both samples contain at least 10 individuals in each category. And yeah, there was at least 10. There were a lot more than 10 on this particular sample. Okay, so now, second part. Does the confidence interval contradict the claim that the proportion of rear end accidents is the same at both types of intersections? Now, I want to kind of do a little note here. Let's take a note. So the population, I'm sorry, not the population. Oops, let me go back. So the proportions are the same when what? When the population proportion from the first population minus the population proportion from the second population. So this is the same as this when you take the difference is equal to 0, right? Because if I said 5 and 5, right, they're both 5. If you subtract them, you get 0. So you know when you subtract two things and the answer is 0, you know that those two things are equal in size. So we want to see if we can get into this. It says, does the confidence interval contradict the claim that the proportion of rear end accidents is the same for both intersections? Okay, so we're going to answer this question right here. It says, because the confidence level, or because the confidence interval contains 0, there's your options right there, contains. Now, how do we know it contains 0? Well, because this is negative and this is positive, so 0 must be in the middle somewhere there, right? So because the confidence interval contains 0, it does not contradict the claim that the proportion of rear end accidents is the same, right? It does not contradict. It does not contradict. It does not contradict because we're saying that the confidence interval contains 0. If it contains 0, well, when it's 0, they're both the same. Okay? So the claim is that the proportion of rear end accidents is the same. So we're not contradicting that. We're saying, hey, we've got a 0 in there, so we're not going to contradict that. We're going to go with it. Let's do the last one. The last problem is talking about pain after surgery. In a random sample of 54 patients undergoing a standard surgical procedure, 16 required medication for post-operative pain. In a random sample of 92 patients undergoing a new procedure, only 10 required pain medication. All right, part A, construct a 98% confidence interval for the difference in the proportions of patients needing pain medication between the old and the new procedure. Okay, there's a lot of information that we need to kind of unpack and sort, and we're going to start right here. Let the population proportion from the first population denote the proportion of patients who had the old procedure and needed pain medication. So I had the old procedure and needed pain medication. Well, let's see if we can. So that's the first population. So that means that the green is that's the old, the green's the new. So they talk about new up here? Yeah, they do. It says, in a random sample, 92 patients undergoing a new procedure. So 92 patients undergoing a new procedure, only 10 required that pain medication. Okay, so if that's the new, then if P sub 1 is the old, then in a random sample, 54 patients undergoing a standard procedure, 16 required pain medication. That must be the old. And they didn't really say old here, but that, we had to do a little detective work to get that. Okay, so now let's start figuring out what we need. Remember what the first thing we need is. Well, first we need to get our sample proportions squared away. So let's start off with this red one right here. Whoops. P hat, that's my sample proportion for my first sample, is going to be 16 were the people of interest out of 54 is the sample size. And when I divide that, I get approximately 0.296. Now I need to get my sample proportion for my second sample. And it turns out that only 10 needed that pain medication out of 92. And that's from my new procedure. And that's approximately 0.109. Okay, now we're going to need our point estimate. So we're trying to get an interval that includes the difference of the population proportion from the first population minus the population proportion from the second population. But a point estimate is going to at least get us started in the right direction. Point estimate. What is a point estimate? Point estimate is doing a sample within that population and then figuring out the sample proportion and then subtracting the two. So it gives us a point estimate. So we're starting off with p hat sub 1 minus p hat sub 2 minus. So let's go ahead and do it now. P hat sub 1 is approximately 0.296 and p hat sub 2 is approximately 0.196 or 109 rather. When we subtract the two, we get approximately 0.187. So this is our point estimate, very important. Next, let's tackle this difficult standard error. It's probably the hardest part of this whole thing. Well, getting everything organized is super important. Now the standard error is just, I guess it's just the longest part of the procedure here. And that's going to look something like this. And we take our first proportion, our first sample proportion, I should say, which is from that first sample, which is 0.296. And we need to multiply that by its complement. And I clearly didn't use enough space here. Oops. Did not use enough space. So now multiply it by its complement. The complement is just 1 minus this red 0.296. And so when I take 1 minus the red, I get 0.704. This is all over my first sample size, which is 54. Then I'm going to add that to my second sample proportion. Now, my second sample proportion was 0.109 times its complement. And its complement is just 0.891 divided by the sample size of that second sample, which was 92. Okay, I put that in my calculator. And I'm getting approximately 0.0049, 146, 043, and so on. Oops. And so we go ahead and take its square root, and we get approximately 0.0701. That's an important part of our calculation that we need for what? We're going to need for this piece over here, which is the margin of error. Okay, margin of error, we can show by saying m, but I don't think I have space for that. So I'm just going to get my critical value. Remember my critical value? I think I used brown for that. Let's do that again. Oh no, I got to go down there. I've got to go down to that Let's use a different color. So remember, my critical value is just z sub half of alpha. Now we need to know our confidence level for this. Confidence level is 98%. We can see that right there, 98%. So let's go down to our formula sheet and look at 98%. 98% is right here. So our confidence level, confidence level is 98%. So our critical value is 2.326. 2.326. That gets multiplied by our standard error, which was just right over here, 0.0701. And when we multiply that, we get our margin of error is approximately 0.1631. And now we're ready to go in for our answer here. What are we trying to do here? Well, population 1 proportion minus the proportion of population 2. We're looking for its upper bound. We need our point estimate, which is right here. Great place to start, 0.187. Just to be sure, we add our margin of error, 0.1631. Then over here, we once again start with our point estimate of 0.187. Now subtract it from our margin of error. Margin of error was 0.1631. And we calculate that. When I calculate that, I'm getting 0.0239. And over here, I calculate this, I get 0.3501. It says please round to 3 decimal places, so we could definitely do that. 0.024. And round this guy to 0.350. There it is, and this is at a, what was this one? A 98% confidence level. Okay, we're almost there. Just need to answer a couple questions right here, and we're ready. You're free to go. So let's go ahead and do this in green. It says, a physician claims that the proportion of patients who need pain medication is the same for both procedures. So remember, they're claiming it's the same. If it's the same, then what? Then that means P1 minus P2 equals 0 if it's the same. So once again, it says a physician claims the proportion of patients who need the pain medication is the same for both procedures. They're claiming that these two things are equal. So we better see what our confidence interval has. Because the confidence interval, well, wait a minute, that's positive and that's positive. So 0 is not in between there. So because the confidence interval does not contain 0, it contradicts. Use a different color, it's getting all tight there. It contradicts the claim that the proportion of patients who need pain medication is the same for both procedures, right? Now, had this been a negative over here, then 0 would be in the middle, and we would say, no, it doesn't contradict, because we would say, we believe, we have evidence that the two procedures are the same, right? Okay. All right, and that is it for today. And that's it for this. Oh, assumptions. Remember those assumptions? Those nasty little assumptions. We have 2 independent, simple, random samples. And it says, I remember seeing that. Yes, each population is at least 20 times as large as the samples drawn from it. And so, like I said, this is sometimes kind of a little dicey to think about. Like, what was the population that we're talking about here? Construct a 98% confidence interval for the difference in the proportion of patients needing pain medication between old procedure and new procedure. So, if that is of the population is of everybody in the United States getting these procedures, yeah, the assumption holds. But like I said, that gets a little dicey, at least in my mind. Let's make that a little bigger. And like I said, they don't really hold us to it in the problem, but I just wanted to go through some of these assumptions. The individuals in each sample are divided into two categories. Yes, there were definitely two categories: new procedure and old procedure. Both samples contain at least 10 individuals in each category. And yes, I do believe they had at least 10, and that's true. Okay, I hope that helped out. And this is the last section, so we're ready to take the test after this. And I hope everybody's doing great. Have a great one, and talk to you soon. Bye.